Hey, hello, Olgi. Ah. Yeah, I'm still setting this up. So, okay. Let's see, because I'm not clear. I don't know where I do want to draw. Yeah. A bit of experience in VirtualBox, yeah. Just a bit. I'm not using it that much. In fact, I haven't used it in the last, I don't know, year. One thing I always have problems with is installing the guest addition in Linux guest. Okay, I don't know why. Usually for me it has been easy. You just plug the ISO into the drive, and yeah, that should be. Yeah, almost. I always use it in Linux, never in Windows. In Windows, I used it a few times, but I haven't done so many virtual machines in Windows compared on Linux. Okay, you got that working then? Okay, let's see how this goes. Yeah, I think. Okay, okay. I mean, I'm still waiting, no worries. Okay, we are ready then. So, I don't know exactly how this is gonna work. So, let's start randomly. Thing is, we need to understand, in order to understand pointers, yeah, I enabled it now. In order to understand the pointers, memory addresses, and you know, all this thing like I don't know, like in C++ that you have in B and so on. We need to understand how memory works. Just think. Wait. Is the camera? Is this my camera? It can be my camera. It can be my camera. Let me check. There is. Camera has. Yeah. It's in my end. Let me see if this works. I need to reset it. No. And now it's frozen. This tends to happen. Now it's now it's broken. Okay, going to hide it. No facecam today. Not working properly. Sometimes it does this thing. So let's remove the camera because it's going to take. Oh, now seems that camera has been disabled. No, but OBS doesn't want me to open the camera. It's totally borked. No, I should have reviewed that before. Anyway, I think that no camera is better than a camera that is 2 seconds behind. Yeah. So it doesn't matter. So the thing is that we need to understand how memory works in a computer. So, let's say that you have your RAM and you have your CPU. And of course, the one is sending data to the other. They are connected. don't know if that line will be visible from stream. It's not that it matters that much. But yeah. So basically, of course, as you might guessed, the CPU needs to fetch data from the RAM, and you have multiple sticks of memory, right? So, but there are a lot of surprises here that we need to go over. I don't want to cover all the details that we don't need to, so I'm going to simplify a lot. So the CPU is the first thing. The CPU has a view of the RAM as a single vector, single array. There is an array. I don't know how to make that. So there is an array, something like 0, 0, 0, 0, 0 ad infinitum. Okay, that represents the memory. And then, of course, those have positions in memory, like in a vector. So you have your position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, a lot of stuff, 997, 998, 999, etc. Yeah, good question. Good question. No, bit is not a type of the array. Almost nothing uses bit as a measure. The minimal measure is byte. So technically that's 2 bytes, 2 bytes, 2 bytes, and so forth. Okay, so you read and write in bytes, not in bits. You read and write in bytes. So that is from 0 to 255. Okay. And then no, 1 byte. So that is 1 byte. That goes from I don't know. Maybe you don't know hexadecimal. Wait a second. So from 0xx00 to 0xff goes from 0 to 255, and that is one byte or 8 bits, because 2 to the 8 is 256. Okay, and this is hexadecimal representation, where each of those is 4 bits. So that is 4 bits. And of course, that contains 8 bits. So far, so good. Okay, let's see. Can I insert table? Okay. Columns 100, rows 2 or 75. Okay. Let's make that 12. So, okay, let's move down. It's becoming bloated. So let's imagine that this is the memory. No, 4 bits, no, nothing is done in 4 bits. This is just because this is a hexadecimal that goes, crap. This is, so yeah, I was not expecting to explain this, sorry about this, my fault, should have understood this. So you have your decimal system that goes from 0 to 9. So the way you count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I mean, so basically when you exhaust, so you have 9 possible digits, sorry, 10 possible digits. Okay, when you exhaust the last one, I'm explaining the most obvious thing because this creates the basis for the next thing. So if the digits are this, okay, when I count, I start using the digits, and when I get to the last one, that I don't have more, I don't have a digit that represents 10, right? There is no way to represent 10 with those digits, with one digit alone. So what happens is then I put the next digit, the first digit, 1, and then the 0. And then I continue counting. So 1, 0, 1, 1, 1, 2, okay? So far, you know how the decimal system works, everyone knows how to count. But now, when you go, for example, to binary it only uses 0, 1. And then in binary, you count 1. Then you don't have a way to represent 2. So then you have to put 1, 0. So you have to resort to the next one, add another 1, another digit. And then the next one is 1, 1, because this 0 can be converted into a 1. And now we don't have a way to put another digit without adding a new one. So now we add a new one, and then it's 1, 0, 0. And then 1, 0, 1, 1, 0, 1. Again, I cannot put here 2. So then it needs to be 1, 1, 0, and then 1, 1, 1, and then 1, 0, 0. Is bigger, so I'm getting out of space. But there is another way to represent the stuff, which is hexadecimal, which is from 0 to F. And the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, A, F. And the way to count this is exactly the same. Just it's a bit weird, because you do 1, 2, 3, 4, 5, 6, 7, 8, 9, but now I can represent, I do have a digit to represent the 10. A represents 10. B, C, D, E, F. So 10, 11, 12, 13, 14, 15. Now if I want to, so this is base 16. That's what it's called, because it has 16 digits. Now that I don't have a digit for 16, I need to use the 0 and add another digit. Then I do 1, 0. Or 10. But this is not or 10. This is actually, so in programming languages, you will see hexadecimal being prefixed as 0x. 0x means hexadecimal. So when you do 0x10, it becomes the first part 1 times 16 plus 0. So the left digit times 16 and the right digit times 1. And this is 16 plus 0, which is 16. You can do this for any particular number. So for example, we do 0xff, this is the first f times 16 plus the next f times 1, which is f is 15, 15 times 16 plus 15. I need to bring a calculator to do that, but this is basically 255. So that's how hexadecimal works. So because it has base 16, it means that if you have a number that is, I don't know, binary number, okay, that has 11010111, okay, it has a, so those are 8 bits. Hexadecimal has a nice property, and the property is that every letter represents 4 bits, because 2 to the 4 is 16. It means that this is exactly what you need to represent 4 bits. So it's nice because you can get what is this number. So number on the left is 1, and this one is times 2, this one is times 4, this one is times 8. So the number on the left is 4 plus, so 8 plus 4 plus 1, which is 13. And then 13, 15, 14, 13. This is D. And then the number on the right is 4 plus 3 plus 2, sorry, 4 plus 2 plus 1, 3 plus 4 is 7, which is basically 7. Which means that now you have that one is D, the other one is 7. Then you can represent that as D7. It is nice. It is nice. I don't care that much how to translate from number into binary, or hexadecimal into number, or hexadecimal into binary. I don't care that much, but it is nice. It is nice because 2 letters in hexadecimal, it's exactly 8 bits. The problem with numbers is that if you use decimal numbers to represent, is that when you have 8 bits, you can have something like 1, 13, or 127, or 255, and it doesn't use the whole range completely, because in fact 3 digits in decimal, this, if we say that we are using 3 digits, you can do from 0 to 999, and we are not using all the range. In contrast, in hexadecimal, you can go from 0x, so from 00 to FF. So remember, 0x is only the prefix that we put in programming. It doesn't have any meaning aside of telling us that the thing on the right is an hexadecimal number. So the cool thing is that we use exactly 2 digits and we cover exactly the range of 8 bits. Nothing less, nothing more. It matches perfectly. So that's why it makes this so good for explaining memory and explaining binary. Because we don't need to talk about bits, we can talk about hexadecimal letters. So we can do, I can skip, maybe I made this too large, or can I just do that? Oh my god, no. Don't tell me that. Align, no. Oh my god, no. Yes, 0x means nothing. It has no particular I'm trying to see. Come on. I'm about to just redo the whole table because this is hilarious. Size, distribute columns evenly. Okay, that does it, but still it doesn't fit the letters. Now it does. Now it does. Okay. Make. So your memory looks something like that. Then D1 F30003. I don't know. It really doesn't matter. It's just data. Okay. What that represents? Really, we don't know. We don't know if those are ASCII characters. We don't know if those are actual numbers. We don't know what those are. It's just data. So without previous knowledge on what this is, it's impossible to make any use of that. Aside of basically copying or... Come on, LibreOffice. We're working so well. I just want to keep copying. Okay. Not bad. Okay, good enough. So, of course, this means that they have a memory address. So this is the first one, the first index. So let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and so on. Okay. So if I ask you, hey, what do you have in memory position 10? You go to your memory, look into your position 10, and you say, I have 0. Or what you have in position 12? You go to 12 and say you have FF, which is 255. But let's say FF. We don't care about the actual decimal value. Let's say this is FF. On 14, I have D1. So you can, like in a regular vectoring programming, you can just locate your data by position. Okay. So far, so good, I guess. Going to wait a minute or so. I don't know. Cool. So now, with this in mind, when we have assembly code or machine code, doesn't matter. It means assembly code is basically machine code, but it's readable. Let me bring something up. Do we have should be able to pull up. Need to pull up some example. Okay, it doesn't show. I mean, the resolution is very poor, but it's good enough. It's good enough. So the assembly code has a direct translation into machine code. So they are equivalent. Then when they are trying to read something, they need to refer to the position in memory. They need to say to the CPU, hey, I need you to fetch data from this location, from FF001122. Okay, this is a number, and this is a location in this array on the top. Instead of 1 byte, there are here 1, 2, 3, 4. This is a 32-bit 4-byte or 32-bit memory address. Okay, which will cover up to 4 gigabytes of memory. So it's locating something in those 4 gigabytes of memory and saying, I want you to read that and store it into the EAX register. Okay, that's because the CPU has internal memory. I'm not sure if you are aware. So the CPU here has now you know. Okay, good. It has registers. It has L1 cache. It has an L2 cache. And sometimes it has an L3 cache. The assembly code doesn't manage the cache handling, but it manages the registers. The thing of the registers is that in order to do a computation, to say add me 2 numbers, those 2 numbers need to be in the registers. So the data for doing any kind of math or operation, whatever you want to do, it needs to be in registers. So what the code does is it's writing it into the register memory. And the registers, those are the fastest memory that we have above everything, because this one, you can access this memory in the same cycle. Basically, it has 0 cost. If something is in the register, it's already ready to be computed. Okay, but if you fetch something from the memory, it has to go to the memory RAM, okay, and it has to issue an order via the cables that says seek to this position and read this data and pull the data to me. And that can take from 100 to 300 cycles. It's very slow. It has a lot of latency. It's not about the bandwidth, because memory has a lot of bandwidth. CPU is fast. The CPU is faster than the RAM, even in bandwidth, but the problem is latency. Issuing the command and waiting for it is very slow. So if you have a lot of tiny chunks sparsed in memory, and you are pulling random parts every single time that is totally unpredictable, it gets super slow because the latency is very bad. That's why we have caches. Every time you pull something from RAM, it gets stored into the caches. So it will get stored into the register, but as soon as you remove it from the register, it will be still stored on the cache. If you ask again later on for the same data in RAM, it will check the caches, if any of the caches has the data, and will pull it from the cache that is much faster than the RAM. This is the idea on the L1, L2, L3 caches. So the lower the number in the L is the level 1, level 2. So the lower the number is a smaller cache that sits closer to the CPU and is faster. So L3 is the biggest and the slowest, and L1 is the smallest and the fastest. And then you have the actual register that you have to fill. That's how it works. So yeah, here you have lots of different registers, EX, EDX. I don't know really the registers. I know that there are registers, and those are registers. The CPU has so many registers. Okay, and you're saying, okay, add this number to this number, do an XOR from this number and this number, and so on, and push left that. So sometimes those also work against one how's it called? So the place where it writes, usually it's always the same register. So if you need to go to the actual book of instructions of assembly for the particular CPU, and they will say for this CPU, when you do add left, add L, it will write whatever you do, the result, it will be written in the register, that register. So probably is the ESE or something like that. The reversed order is because MDNS. You mean here on those things here that this is reversed from here? The number is in reverse. Is that what you mean? in this mov-l that the address appears. Yeah, that is in DNS. That is in DNS. This seems to be assembly for how's called is the like the x86 like or computers, regular computers, AMD and Intel, that are the little endian. Now has come to my mind. It's little endian, which means that we put this thing, the numbers in reverse, and it starts by the little endian means that it starts by the least part. Yeah, little endian. It starts from the little and ends with the big part. Big endian will not reverse that. Yes, that is in DNS. Yeah, but it doesn't matter. It doesn't matter for a lot of stuff. Yeah, it really doesn't matter. As long as you know where you are, it doesn't matter if you are in little or you're in big. There is some operations that are faster in little, and there are some operations that are faster in big endian, but the benefits of each one is so marginal that I don't think it makes any difference in reality. So it's just that some platforms might have it reversed, whatever. So, as I was saying, okay, so you see that in order to fetch data from memory, you have to refer to the address of the data, right? That's why. So this is called the memory address. No, insert text box. I'm getting. Oh, I lost it. So something like 0xff010203. Okay, that's a 32-bit address, which is up to 4 gigabytes, or things like 0011223344556677. This is 64-bit. And this memory address is up to a lot of numbers. Those are 2 exabytes, which is a lot. So you can reference up to 2 exabytes of memory. If you install an operating system that works only in 32 bits, the operating system can only access up to 4 gigs of memory at the same time. Programs can only access 4 gigs of memory. Or if you build for 32, you can only access up to 4 gigs. If you build for 64, you can access up to 2 exabytes. So yeah. So one will think, no, you might think that when you request in assembly, one memory address represents to a physical location in RAM. In fact, the RAM modules are loaded in a particular order. Yeah, it's physically impossible, yes. You cannot use more than 4 gigs in 32-bit. You cannot. There is some trickery, but it's very bad, and regular builds will not be able, and the trickery is not sure if it actually works. There is some trickery for operating systems to make use more of 4 gigs for the operating system, but I think the trick doesn't work for programs. So I think that a 32-bit operating system that is prepared for 64-bit, that has a trickery, can have more than 4 gigs of memory and can use them, the operating system, but a single program cannot use more than 4 gigs. So, I mean, you could have 2 programs with 4 gigs, but yeah, a program cannot use more than 4 gigs in 32-bit. and the OS, most OSs also cannot. It's just that there was late in the history of Windows and Linux on 32-bit builds, there was a patch to make this work, to have more memory, but that lasted maybe 2 years. It lasted. Very bad trick. So yeah, so the RAM sticks are loaded in a particular order, and then if you have, I don't know, 1 gigabyte here, another gigabyte here, and so on. So probably the first gigabyte is here, the next gigabyte is here, and the next gigabyte is here. That really doesn't matter, but it has a particular order, and also depending on platforms, it will be different, but that really doesn't matter. But the thing is that a memory location will go, in theory, at a particular point in one of the RAM sticks. Okay, that's understood so far. So now I think I'm going to blow your mind on the next part. So, if you have, let's say that you have 2 programs. Okay, imagine that we have 2 programs running. One writes to memory address 0x10. The other reads to memory address 10. What happens? So here is the trickery. Those 2 memory addresses are the same number. Okay. And then previous operating systems like Microsoft DOS and not Windows 95, I think. Operating systems from the 16-bit era. Those 2 programs running against the same memory address, they will have one will write the data and the other will be able to read the data from the other program. And therefore, from one program, you could break the other program. That happened several times when we were in Microsoft DOS. But nowadays, this is not true. Turns out that the programs don't access RAM directly. They access virtual memory. And the virtual memory is just kind of a scratchpad. Let's say there's a scratchpad, I don't know. That maps to actual memory. There is a mapping, something called the MMU, I think. This maps the virtual memory pages into RAM pages. 4 KB, I think, are the pages. So basically, what happens is that they go and they say something like, let's see if I can get something. No, I'm looking for something. Found you. And now rotate. Cool. I made a copy by mistake. So what this MMU is doing is saying, like, from here to here, that goes. Let's put a proper text. your virtual mem address 0x100. Why my widths are so thin? Come on. No, that is very thick now. I never understand the default selection of those programs for fonts and sizes. They are so bad. And now we can take another block and say this block is for program 2 for the same virtual memory address. Let's say this with memory address 10. Yeah. Okay. So you get a picture. So there is a mapping. There is a table. There is a table that is mapping virtual memory into different chunks. So even if two programs are trying to access the same memory address, in fact they are being mapped into different regions of the memory. So far so good. So this virtual memory thing isn't that mind-blowing. Is that what you meant? Yeah, I just what I meant. Can I expect something like that? We will have in second. It wasn't that safety memory like that. Okay. So that was started with the 32-bit architecture. The problem was that 16-bit architectures don't have enough space to have these kind of measures. It's like also 64 bits architectures have some additional measures in security that actually use the 64-bit, that use the other branch, which is I think the ring 0, ring 1 and so on that the CPU have. They have different CPU modes. 64-bit is what allows you to do virtual machines that are roughly fast without compromising your computer, because in 64-bit you can kind of create a sandbox for the virtual machine, for the code, and you can execute the code natively in your CPU without actually worrying about if the code is going to try to break off from the VM. It can be executed natively, because anything that might potentially break from the computer, from the virtual machine, will create an interrupt, and it will be catched and it will be audited and handled. So there are just a few operations that are slowed down, but raw computation, what is the raw computation, data fetch and so on, can be executed natively in 64-bit for a virtual machine. If you have virtual machines running in 32-bit, that cannot happen. I'm talking about the host, about the actual computer that has the virtual machine. Not if the virtual machine is emulating a 32-bit. That doesn't matter. The thing is that the computer holding VirtualBox, for example, should be 64-bit in order to have those security features, and then it can defer the execution to the CPU. So yeah, as we grew in the architecture, we are increasing the amount of security that we have on the computers. So yeah, the thing is that the virtual memory No, it doesn't matter. You can make it 32-bit. It doesn't matter. What matters is that your operating system, where you're running VirtualBox, your operating system needs to be 64-bit. Your CPU needs to be 64-bit. So you need a 64-bit VirtualBox to run, and then you can run inside VirtualBox a 32-bit or a 16-bit machine. That is totally fine. The problem is when you want to run, I mean, if you wanted to run a virtual machine inside a virtual machine, then I think you're a bit out of luck. That's not a very good idea. But as long as all of them are 64-bit, all the builds for VirtualBox are 64-bit and the operating system are 64-bit, it runs kind of fast. If you have a computer that's 32-bit with a VirtualBox 32-bit build, it will run painfully slow. I'm not sure if they will provide a 32-bit build anymore. So yeah, this is kind of the thing. So yeah, the next shocking thing is that the virtual memory in a program is always 2 exabytes in size. Win 10 still has 32-bit. Oh my god. They should go home. Force everyone to migrate to 64-bit. For the love of God. So yeah, the program, because it's virtual space. Yeah. Try with a 64-bit one. Yeah. 32-bit builds, they might be barely working. I don't know. I don't think they are giving them almost any kind of support at all. So with no support, I don't think it's a good idea to run them. Work error? Is that in your end? What? Can see I'm streaming. For me, this is. For me, it's working. Yeah, I can. Of course, I can. Oh, it's working now. Okay. So yeah, the okay, what was then? Your question is that if it's worth trying a 64-bit guest? Yes, try a 64-bit guest. That is worth trying. A 32-bit one, I don't think it has support anymore. I don't think they are putting any kind of care into that. Okay, so the virtual memory in a program is always 2 exabytes in size, even you use it or not. So it's like you have access from 0x, let's say 1, 2, 3, 4, 5, 6, 7, 9, 10. So you have, you have the 16, so 64 bits available. Okay, all of them are available for your program. When you ask for memory, so you cannot read or write. Oh, sorry. You're hitting Matrix through the stream. Sorry. It will be easier if I can disable entirely the sound. Crap.
Don't you ever walk away.
Yes. Of course, you will be hearing it. Yeah. No. That was Matrix. That was Matrix. I just disabled it. Yeah. That was Element. That was Element. You were writing me, and it was popping the notification, making the sound. So okay, so far you are following this. So, and the thing is that you cannot read or write any random location, because if it is not mapped, yeah. If it is not mapped, it will cause a segfault. I guess it puts it always as far left as possible. No. It's more complex than that. It's way more complex than that, because turns out that in memory, in memory, you don't have only memory. You have other stuff, like devices, I/O, kernel, etc. Is the virtual memory a vector of smart pointers? That will depend on the operating system, what it is doing. You will need to see what Linux is doing exactly, or what Windows is doing. And each one is free to do it in a different way. So, but yeah, it is managed like a vector, and it is smart, yes. So, for example, the kernel may place itself in a position like from 0,0,0,0 up to 0x, something like that. Call a function like open file. It will be incredibly cool to have a simulation for different approaches. Oh, how operating systems manage memory, that is really complicated. And they are also evolving over time. So my understanding might be even old, very old, and incorrect. So yeah, So your program memory may start at 0x200 or something like that. Or whatever. Okay. In order to use memory, you need first to allocate. And then in C, this is something like something called malloc, where you can put here allocate 3000 bytes. So this is a kernel call. Okay, goes to the OS. Okay, and this will make the OS look for a space of 3000 bytes in RAM, and also look for a 3000 bytes space in your virtual memory, and create a map between those two, and say, okay, now this region of memory from here to here now belongs to this program. Yeah, I scroll down now. So yeah, after that happens, so P will receive a number that is the memory address, something like 0x10fe32. Okay, and now you can write into it. So you can do star P, which means the content of P equals 555. Okay, and this will write 555 into the first 4 bytes that we requested. 4 bytes because it was int. And you can also treat it as an array. You can also say P10 equals 1, 2, 3. So this will get the 11th element. Oops. For the love of God, what? After the 0x10fe32. Or, in other words, it will compute fe32 plus size of int times 10, and use that memory address instead. So roughly, I'm getting into how works memory in C right now, but yeah, basically what we are doing here is that if you allocate all the memory and those are ints, then ints of 4 bytes, then the first 4 bytes. So from 0 to 3, this is the first number of the array, and then this is the next number, the second, this is the third, this is the fourth, and then you can compute the memory address of any of those if you get the position of the first element, that memory address, and you add how many elements you have times the size. The size is 4, and then you do element 10 times 4 is 40. You will be scrolling right until you find 40, and that will be the memory address to the element that you are trying to access. And of course, that needs to fit inside the 3000 bytes that you allocated. Because if it doesn't, it causes a segmentation fault. It crashes the program. Okay, every time you try to read or write outside of the boundaries that you have been allocated, your program crashes. One exception is that if you are unlucky enough that you have another variable, let's say you have int q, and you did another malloc, and maybe the OS can allocate this just after P. That can happen, or might not. That's just random. It's possible that the program, instead of crashing, it might be writing on Q, and that will be also valid. Yes. Something is on your mind because this is connecting a lot of dots right now, and something is starting to make sense right now, and you may be forming right now a question or something. But this is just introductory. This is just introductory. I'm not trying to give a masterclass here of anything. It's just basics. So I want to have a look to this image here. Let's move it over here. So when you run a program, you have two types of memory. You have the heap memory and the stack memory. When the program is started, the program is the instructions of the program, so the assembly code, is loaded into the memory program. Let me read. Can you tell me, show me why U64 is slow on 32-bit and why U128 is slow on 64? So it might not be that true anymore. It depends. It depends on the actual CPU that you are running in. So the problem is that the registers usually are in a CPU are usually the same size as the architecture. So the registers usually are 64-bit in a 64-bit architecture. So this means that if you need to do a multiplication or something in a 128, you will need multiple registers. And also the operations is typical that you will not get an instruction to do a sum or a multiplication with 128. Then you need to do several rounds. You need several cycles to process the data. Nowadays, CPUs do have data and registers and stuff to handle up to 512 bits at the same time, which is called SIMD instructions. So I expect that they are able at least to read the data from two different registers together and do the instruction in one go. but an old CPU, an old 32-bit CPU, is unlikely to have an instruction that is able to do a 64-bit in one go. So you will need in assembly probably 2 loads. You will need to load 2 times in order to load one number. So that means 2 instructions to do one thing, to do one load. And then to add them together, probably you need 2 to 3 instructions, I guess, to finish the computation of the number. But on the other hand, if should I think of U32, U64 as minimal values? Yeah, in reality, you don't gain much speed by going lower. So in a 64-bit architecture, if you put a 32-bit data, the register is 64 anyway. So basically, you are using half of the register, and you cannot put 2 numbers in one register. That doesn't make any sense. So in the end, they are processed at the same speed. The only difference is that if you have a ton of data, if you have a ton, like a million of the same of the 32-bit values, they are going to use less memory, and because of that, you're going to use less bandwidth, and it's going to use less cache, and that is very probably going to speed up things. So when you have a lot of data, it does matter what is the size of the data. But if you have a tiny amount of data that you just doing a lot of computation, a lot of cycles, but across very tiny amount of data, then the difference becomes negligible. So negligible that is mostly the same. Minimal isn't guaranteed to be fully supported. Yeah, I mean, if I'm already, again, you know that I'm a bit against supporting 32-bit. There is less and less on the days that today to do 32, but there are still machines. In architectures that use less than 32, like 16 or 24, just forget about those. Forget about those, not because there is, not only that there is almost no one using them, is that the memory layout, what they explain here, how memory works, has nothing to do with a 16-bit architecture or 24-bit architecture. Those use a complete different system. It's not a memory as a vector. They have other stuff called near memory and far memory, and it is a freaking hell, and they don't have proper operating systems. So an application that runs in something smaller than 32-bit, most likely, even if you make your integer 16 bits, even with that, it's not gonna run. It's not gonna run because you will need a ton of work to make a program run in 16 bits. Because everything, all the chains, all the tool chains, everything, all the tooling is prepared for 32 and above, because it's when all the memory became a holistic thing. It became a single thing. We started having virtual memory. We started having a single memory vector, and it's when things started to make sense. Before that, it was every platform. It was totally different, and building something for multiple platforms, it was super painful. And today it still is to build. Is very painful to build for any 16-bit platform because they are super different. So go for U32 and sometimes U64 if you need it, because 32-bit processors can handle 64-bit operations just a tiny bit slower. So as long as you're not doing a ton of operations on 64-bit, that will be fine. And yeah, and no need to worry about less than that. You're not going to give compatibility to anything else. Even if you go lower, you're not adding any additional platform. You're not gaining anything. Like if you go lower, we'll be talking about microcontrollers, I guess. And even microcontrollers nowadays are 32 and 64 bits even. But any program that runs in a microcontroller, you need to write it ad hoc for that microcontroller. There is no portability. So your program is not going to run a microcontroller unless you recode the whole thing. So yeah, that's what it is. So, I think we are back from where we were, and we can continue, yes? Recapping on this, okay, let's see. Okay, very quickly. So yeah, as I said, the virtual memory in the program always has the 2 exabytes in size, even you use it or not. Okay, and you have all 64-bit available on the program to put pointers into. Okay, but you cannot read and write into any location. Okay, if you try to read and write to a location that is not mapped to RAM, it will segfault. It will make a segfault, so the program will crash. Okay. Yeah. I realized this. So segfaults are related to the MMU, the table mapping, and also to interrupts. But yeah, basically a crash. And also in the memory, you don't have only memory to access. You have other stuff like devices, I/O, kernel functions, and other stuff. So for example, the kernel, you can have the kernel placed in a position in memory, for example, from 0 to 1000, in such a way that you can call the function open file from the kernel. You need to know where it is. It needs to be loaded in memory. So the kernel might place itself in some range of the memory. And the devices can be also in memory and any kind of input output. Yes, because you can only access 4 gigs of data. So let me show you something. Let me show you something. I can use this, I guess. One sec, what it is? Ah, here it is. So, my trusty calculator. So if you have 32-bit, okay, you have the amount of stuff that you can address. So the biggest number that you can write is 2 power to the 32. This is the biggest number that you can write. So this is how it works. So this is the base. So let's say that what is the biggest number that I can write with 10 digits with base 10 or 5 digits? So we do 10 for base 10 to the 5. Okay, this is the biggest number that I can write with 5 digits. Okay, because it has 5 zeros. In the same way, if I do 2 to 32, 2 because it's binary, so it's base 2, you only have 2 options. You have 32 positions, so 32 bits. You have those are millions, those are billions. You have 4.2 billion numbers that you can fit in that. So if that number, if those are bytes, so if each index is 1 byte, okay, this is the maximum that you can represent is 42.29 gigabytes. But if you go to GB bytes, that's exactly 4 gigabytes. And in reality, it's less. It's less than that. It's less than that. Because as I was saying that the kernel places itself in a range of memory, and there is other stuff that you need to have in memory as well. The range is even less. So sometimes it's 3.5 gigs. So mm, 3.5, yeah, because kernel and needs to be in that virtual memory. So that is the maximum. That is the maximum. If you build for 32-bit, it needs to fit in those 3 gigs or something like that. So yeah, as I was saying, the your program, the memory that you can use might start at 2000 or any particular number, so you don't know. And in order to use the memory, you first need to allocate it, like request the memory to the OS, okay? And that is a function called malloc that you have a manual in here that explains, okay, malloc, free, calloc, realloc array, or allocate on free dynamic memory, okay, that this is calling to the operating system to say, I want to ask for this amount of bytes, and the operating system returns you what has been allocated. So where is the data allocated? There is free. So those are C functions. That works in C and C++. So you can use malloc to ask for the memory and free to release the memory. And that is totally manual. But that's how it works. That is a kernel that calls to the kernel internally. Calls to the operating system. So in Windows, it will call to Windows to ask for the memory, and in Linux we'll call Linux, or in BSD we'll call BSD. So yeah. So yeah, you need to allocate it in order to access it. In order to write to a particular memory address. You cannot write or read randomly to random places. You need to read to that. Okay, and then you can write to any part you like on those 3000 bytes that you requested. You can do whatever. Okay, that is more or less it. That is more or less what I wanted. No, you will never use malloc. You will never use malloc except if you want to try it yourself in a C program. It's good to know that it exists, that is how it works, but no. Malloc is too manual to be used unless you're writing, I don't know, kernel or something in C that is very low level. This is, in C++, malloc is not used. But C++ does have the malloc equivalent. Oh yeah. Yeah, let's do a 5-minute break. Let's do 10 minutes. Okay. And I am back. Hey, hello, Alki. Oh, works again in Twitch. Good. So, as I was saying, because... Oh, no. I didn't. Let me check. Cool. I just saw it, yeah. Yeah, there is malloc. There is malloc. I mean, in this kind of programs that they are doing so much stuff that is so low level, so manual, is more than normal that you will find malloc over there. They are doing so all that code looks like memory magic. It's all sorts of magic for memory handling. So yeah, makes sense. Makes sense. So malloc also exists in C++, not only as malloc, but as a specific keyword for C++. In C++, you can do something like int p equals new int 256. If someone happens to see this... Oh, I'm not following right now. I'm not following you. What happens if someone sees that? What is your... Okay. So you are just adding context. Okay, yes. So that was the file that we were looking at. So, okay. So the new keyword in C++ just calls malloc or similar. To reserve memory for the requested type. So basically, you will say, I want an array. So I want to hold an array of 256 integers. Will compute how much it needs, and it will call malloc for you, and it will return you the memory address. That's in C++. So, and the new keyword, you will see it sometimes in C++. But yeah, this is minor. The important thing here is the concept that you request memory in order to access it. They give it to you, so the operating system gives to your program the memory address to use, and then you can use all the range that you requested. Not only that particular memory address, but also everything on the right up to the size that you requested. So if you request 256, you can do p come on, p plus equals 1, and that will increase the memory address by 1 int, now pointing to the next item. Then you can do and this will store 1, 2, 3 into the second item. But I mean, this is complicated. I'm just saying that you can do a lot of weird magic, weird stuff with pointers and memory addresses, because in the end they are memory addresses. You can just change the memory address, add 1 or add 4 or whatever, so point a bit more to the right, and you can access that one instead. So you can play a lot around that. This is the basic idea. So with that in mind, going to want to go through this. Any questions so far? I guess no. Okay. So. Yeah, that is good enough. I'm just doing an overview. I don't want you to understand in depth everything. I'm explaining far more than I really wanted to, so no worries. Your current understanding should be good enough. So when your program loads, so basically when you call your program to execute, your program will load into memory, okay? And that will include instructions, so the actual code will be part of memory. So it's not the memory is not only the part of memory that you are actually using for variables. Your actual code is using memory in RAM as well, so because the instructions are stored in RAM. So the instructions will be stored in RAM. Then you will have the literals, which basically those are the constants. Every time you write a constant, and the constant is, for example, every single number. When you go here and you write the number 555, that is a constant, and this number needs to be stored in the binary. So in the binary file, it is stored, and is also stored in memory. There is a region where this number will be stored, or that number will be stored. Not only when you write const. If you write const as a constant, is stored in memory, but also when you write the number down, it's also stored in a region in memory. So all those are constants. Those are called literals. So the literals part contains all the data, all the pieces of text that you write between quotes, all the numbers, everything that you write that is not particularly code is considered literal and is in here. Plus static data, more or less the same. This is also constant values and static values, things that are have a particular value on the beginning of the program. And from there, when you exit that region, you have the free memory, okay? That is 16 exabytes or whatever, 2 exabytes long. And here you have two parts of memory. You have the heap and the stack, and this is the part that you need. I need you to put attention. So every time we do malloc, we request memory to the operating system via malloc, via the new or whatever. So every time the memory is requested, it goes to the heap. So it will keep growing up. Okay, but every time you call a function, the functions you need something called the stack. Functions, let me go over VS Code. I don't have anything particular right now, but I mean, I can just open any program. It doesn't matter which language or what it is, but when you call a function has inputs and the return value that is the output. Those inputs, those variables, that goes to a special part in memory that is called the stack. Also, when you write your function main, where is my function main? Here. When you write your function main, for example, and you do let x u64 equals 0, okay, that also goes to the stack. So all the variables that you declare normally and the function's data, that goes into the stack, into this region of memory. This region of memory is the stack, and that is where your local variables are. And this, as you call a function within a function within a function, or you have a recursive function, the stack keeps growing and grows in the opposite direction as the heap is in the other end of the memory, and it keeps growing as you call more functions and more function. Oh, sorry, I didn't transition. Thanks. So yeah, as you call the functions, the stack will be getting full and full and full. It will get more and more data as you call a function within a function within a function, and we'll be getting more and more data, and will grow more and more and more. And as you return from the functions, when you're returning from the functions, each return will be emptying the stack, and the stack will shrink. The stack sometimes has a maximum space, has a reserved space from the beginning of several megabytes, and it is possible to overflow it. So if you call a lot of functions within a function, or you have a recursive function that never ends, it keeps adding stuff into the stack until it no longer fits because it has a maximum size, and then you get the famous Stack Overflow, famous because of the site stackoverflow.com. So Stack Overflow means that you're calling too much functions inside functions, so much that you overflowed the area for the stack memory. Okay, so in programs, you want in the stack, what you want in the stack is the variables that are small, that they have a regular size, they are not big. And if you have some data that is big, that is kind of huge, you want to use the heap instead of the stack. In order to use the heap, you use malloc, and then you request the memory manually and you free it manually. So to put in perspective, that goes into the stack. Okay. If I do a vector, an array, I don't know, U64, 200, and we put here this also goes into the stack. Okay, so this is in general, it is a bad idea to make very big arrays because it goes into the stack and you can overflow it. So 200 is small, even for the stack is small. But if you have a recursive function that, of course, is recursive because you call the function, right? And you have something like this inside the function. In each recursive call is going to declare a new one. Another, I don't know, that's 1 kilobyte, 2 kilobyte, almost 2 kilobytes of data per call. And if it keeps recursing in, because of this one, it might do Stack Overflow much quicker because it's recursive. So that's something to consider. But usually 200 is not too bad. I mean, it's pretty small. For today's standards, very small. But you could have something like this, I don't know. And then you can enter into a problem and you can cause Stack Overflow because of that. On the other hand, things like a vector you can make it pretty big, and the vector will be stored in the heap. So this is a stack, and this will be stored on heap. So technically, the variable v2 is in the stack, but because of how vector works internally, the memory is allocated in heap. It does a vec, so the vec internally will call malloc to allocate the space for the size that you are requesting, which is good because then you can request very big sizes and you don't need to care about the Stack Overflow. v2 is still on the stack, but not the contents, only the pointer. Okay, so there is this difference between stack and heap. And also there is also box in Rust. If you do box new, yeah, my fingers today are not in the correct place. I just think it might be the picture that I was displaying. Wait. One second. Should appear soon enough. So yeah, this was a stack, and box is just moving to the heap. Anyway, I think this is the explanation. There is nothing more in here. You can tell Rust if you want in the stack or in heap. In C++, What the graphic represents is the memory from bottom to top. So basically, it's representing so like from the memory address 0. So so very bad choice of colors, I guess. Very bad choice of colors. Okay, so it's like from the start of the virtual memory address of your program. So the first pointer you have, it begins with the instructions, and then the literals, and then the static data, and then there is the heap region, and then from the end there is a stack. What is the square? Wait, which is square? This is full of squares. What if I make this? This is going to look weird. Wait a second. Maybe this will... They are about the same size. Which color? Or you mean the combination? So when we have the memory as a vector, this is what it refers to. This is what it refers to. Like when you have your memory with memory address 0, 1, 2, 3, it means that first you begin with instructions. So you will have, your memory will start with instructions. The data will be instructions. And then after that, those finish, you will continue seeing in your memory, in your virtual memory, your program will see the literals, the constants, and the static data. And when it continues, you continue to the right, you will have the region for the heap memory. And then at the end, you will see the stack. So if all of that was the memory of your computer, this is something like that, right? I mean, it looks horrible, but this is the idea. They represent regions in memory. So it is like a vector with a fixed size where some stuff gets pushed left, instructions, etc., static, dynamic, and the stack gets pushed right. Oh, almost. Yes. Yes. There is one caveat to what you said. So the stuff that gets pushed left, sorry. I mean, that doesn't matter if it's pushed left or it's pushed right. The stuff that is pushed is just the heap. The data below the heap is totally static. It cannot change. When the program starts, when you start the program, all the first 3 blocks get preloaded. So the operating system will preload instructions, literals, and static data from the binary. Your binary will be basically copied into memory, and your binary has those regions. Okay, so the binary gets copied into memory, and then when the binary ends, which is on the static data, then from there starts the heap. That this one is the heap is the one that grows. The heap grows up or left or right. Doesn't matter. The point is that it grows in one direction, and the stack grows into the opposite direction. That's how it works. Those two, the stack and the heap, grow towards the middle, which is the empty memory. Yes, correct. Correct. I'm not sure if that is the best choice of words, like a tuple of three constants, but that is correct. Like with your own wording, because that's your own wording that might not be technically correct, but that is correct. You got the idea right. That is correct. So, well, also in memory you will have other stuff here. So you will have this picture, of course, is incomplete. You will have here the kernel as well. But in practice, does it matter really? Does it matter? Doesn't matter that much. But there is a fraction of the kernel that is also in memory as well. Because, you know, when you want to open a file, you need to call the kernel. And how to call the kernel? So you need to call a function that is not in your program. It's a function that is in the kernel. To call a function in the kernel, you need the kernel in memory. So kernel or OS like Linux or Windows will be in a region before your program instructions as well. So you can open a file, close a file, or open a socket for networking or anything that requires an operating system interaction. But yeah, the point is not to be precise, is to get an approximate idea on how this works. Because now I can go into actual code. So then let's revisit what I was talking to you this afternoon. So let's say we have an integer with a value 0, okay? And where it is? Okay. Okay, let me see if I can locate it properly. Here it is. Yeah, and we have the failure. That's correct. My C++ code looks actually like C. So so yeah, I'm going to code more C than C++. Must return integer. Okay, you win. I thought that was possible in C++, but doesn't want. Okay, in my days this worked, but since that not anymore. Oh no, it's not better. It's older. Printf is C. Is the C library. It's not. This is not C++. It's just C. You can use it in C, and I just totally hate C out, C in. I just hate it. I hate all the C++ standards. So my C++ is basically C with classes. That's why if someone asks me like, "Do you know C++?" I say, "No, I don't know C++. Sorry." Because my C is C with classes. That's what I code. So yeah, that returns value 0, or we can do value plus 5. So far so good. Okay. Now let's say we have a pointer to value. Okay, and then the type is this. Don't be misled that the star is with the variable, because the type is that is an int star is the type. The problem is that C and C++ they are weird when doing this. They are weird because they associate the star with the variable. But yeah, that creates an int star, like a pointer to integer. So now I can put here. So I can put here 0 technically. Okay, and I can print for C, C++ and Rust, what? The star association with the type, that is only on C and C++. In Rust is different. In Rust the type is that exactly. It's not associated to the variable. I mean, doing that in Rust is already unsafe, so I'm a bit not 100% sure, but I think that it makes more sense. Okay, so yeah, value is 5, p value is 0. So it's basically a number. So this technically this is a memory address. So this is a memory address that I can put 1, 2, 3, and because this is hexadecimal, now it's going to print. It doesn't like it. It doesn't like it. It's telling me that. Come on, eat that. Yes, you can force it. You can force it. No, yes. I want to store that I want to store an integer into a memory address. That's what I want. And now you have the decimal value. But no, I do want the hexadecimal value because it's a memory address. And now we have the 1, 2, 3. You can put here like how many zeros. And we have here the memory address. We can put the 0x on front, and it looks like that. So yeah, of course you can do that. And now you don't get 124, you get 127. We'll go over that later on, but you can add. It did a +4 instead of a +1, so it's doing 1 times 4 because int is 4 bytes long. Yes. Now we will revisit that later on. I don't want to confuse you more than needed. Now we're gonna store here the address of value. Okay, so this is ampersand is the address. Now if I do that, okay, we have the memory address of the value. Yeah. Oh, well. That is a good symbol. That is a good symbol. They could have done that. I don't think they use the at thing for anything. I don't think that means anything. So yeah, they could have designed it in a different way, yeah. Now, I can go and say p value, if I add 1 here, is going to change the contents, which is the memory address. So it's going to change the memory address. But if I want to change the contents of this memory address. So I want the computer to access the memory address. Also, have you noticed that every run is different? We have a different memory address in every single run. This is a security feature from Linux that is quite recent. That is memory randomization or something like that. But every single execution gives you a different memory address. That's a security feature. So if instead of adding 1, we want to change the contents, we put the star at the left. So this star is the referencing. So let's put here. Means the reference. Access the memory address in that variable and get the contents. Yes, you want to edit or read, not only write, also read. So now, yeah, that's what the reference means. Value 6 instead of 5 because we changed that. But you can also access star p value, that will be an integer, and I can read it normally. Yeah, that's why I'm doing this stream for you, so you can understand all this kind of stuff. And for the sake of completion, let's put the memory address of value directly. You will see that both hold the same memory. If I put here int value 2, let's put bar equals 33. I could also have here bar, and bar. Okay. And we see that value and bar are one next to the other. In fact, bar is on the left. Yes, bar is on the left. So here comes the trickery, because bar is on the left. Oh yes! Oh yes, this is unsafe in Rust. Of course it's unsafe in Rust. I mean, it is not unsafe because you can do kind of the same thing in Rust without using unsafe, but you cannot access the actual memory address. Well, you can read it. You can read it, and you can dereference as well in Rust without being unsafe. That's totally safe. But a lot of the trickery that you can do here in Rust is totally unsafe. You need to use unsafe to do a lot of this stuff. If I now do this, yes, read-only is good. When you write, is the problem. When we do this, this is a problem because the previous memory address is not guaranteed to have data, but we saw that bar seems to be stored on the previous one. So my guess that is going to change bar instead of value. Here you go. Instead of adding to value, it has added to bar because I subtracted 1, and now by mistake, let's say, instead of changing the contents of value, we are changing the contents of bar. Because it's the address that is next to the other address. But that works in my machine. If I put the program and send it to your machine, or into a different compiler, instead of C++, I use Clang or another Intel compiler or Microsoft compiler, they might rearrange the variables in a different way, and this stuff might break. This magic here might break completely. Yeah, C++ should be GCC. Yeah, GCC 12, yes. Yes. I think this is just a wrapper on top of GCC to make compilation easier. There is no manual for C++, so it's probably GCC with some pre-baked flags to make compiling programs easier. Okay. So far understood, right? I'm going to make this a bit smaller for me. If not, I cannot write anything. Let's say we have a function that returns void that says add 1, and we pass an integer var1, and we do var1 plus plus. Okay. If I go let's comment that out. If I go and I call add 1 with value, okay, what is going to happen is that this value, which is going to be 5, okay, it is going to be copied into the function. Okay. The function arguments usually are registers. So what happens internally is that value is being pushed into the registers of the CPU, and then it jumps into the function. Okay, so you got a copy of that variable. So this will add 1 to that variable, and then will return. But because this is a copy that sits in a different memory address, this variable will disappear. So this variable will be sitting in the stack, and once you return from the function, when you exit the function and come here, this variable disappears from the stack. It gets freed and basically disappears. So the changes also disappears with that, because this is not this, is a copy. So your program yes. Oh yes. But I want it below, so I can put there, and that will do. This is one of the things that are nice in Rust, that you don't need to you don't need to do it in order, but in the C++ compiler you need to put them in order. So yeah, this doesn't change. You're following. Good. Let's print here var1. I know that it's pretty basic so far. You know this. That's good. Yes, you put here a struct, a vector, whatever. It is copied. It is copied. Always copied. Okay. So var1 becomes 6, but it has a different memory address. It's very similar, but the last 3 characters are different, because those are different positions on the stack. So that is the stack. Those are different positions in the stack. So structs have to be in order. Yes. Pretty. This is pretty lame. Yes, I agree. But the C++ is very old. So back then that wasn't a big deal compared on the advantages of using C and C++. No other language was doing better back then, so it was the best 40 years ago. So let's say we want to change the original thing. So what we do is, instead of accepting the raw variable, we accept a pointer, a memory address. So this is p value is a pointer. Okay, that's called a pointer, because if it contains a memory address, okay, so no, don't write that. Okay, it is called a pointer. Okay, that's so we convert into a pointer. So we want a memory address. Okay, by placing the star. So now this is a memory address because we want the memory address. So if we try to run this, okay, we need to add it here as well to the definition. Okay, so it's saying you are trying to pass an integer, but this is expecting a pointer to integer. That's not valid. So you need to do ampersand to extract the memory address of value. And then we pass the memory address. Okay? Now what happens? That this is a memory address, and we added 1. And then we are printing the memory address, and we are printing now the memory address of where are we storing the memory address. So in fact, ampersand var is of type pointer int. Yes. Rust borrowing is a bit strange, if that's what you refer. I mean, this is simpler than what Rust does with borrowing. Borrowing takes a bit more effort to understand because it has a layer on top to ease things, and it gets a bit confusing sometimes. The good thing with borrowing is that you cannot screw up without the compiler screaming at you, so it has disadvantages. So yeah, so now here this is basically a star int, like a pointer to a pointer. Pointer to int. So now you have that because this one is type int, and then if we do star var, that one is type just int. Okay, so this one is a memory address, so we should print it like that. And if we want to add one, we want to add one to the contents, so with the reference here. So that, so you can see. So that will convert int in a star int, let's put between parentheses, into int, then add 1. And now the other one has, you can see it outside. I don't know. How is this explanation? Is too much? It's just right? I don't know. There was something else that I didn't. Okay. There was something else that I need to try because I didn't use that much when I was using C and C++. let's call it at 2 instead of at 1, at 2. So, and let's call it var 2. Let's say we want to do this, okay, but we want to move the effect outside. If I'm not mistaken, so we want to add 2 instead of 1. Yeah. So I think you can do this. And then bastante yes. Okay, you win. I'm going to move it up because I don't want to keep updating the declarations. Yes, this also works. You can put just an ampersand. This is what is called what we call syntax sugar. This is what we call a syntax sugar, meaning that the compiler internally is doing the same as the add one function. So syntax sugar, when we say syntax sugar, it means that we have a special syntax that is basically equivalent to a different syntax that is more verbose. So it's a shorter syntax to do the same. So when you put, but that only works in the function arguments, if I'm not mistaken. If you put the ampersand in the function arguments, it says that yes, this function will work with a memory address instead of the actual variable, but you will work with it as if it was a regular variable, and you will call it like a regular variable, like a regular function with a regular value. And the compiler will adjust it to pass here the memory address. So you get the idea. Internally, the compiler is doing this. Internally, the compiler is putting here the ampersand, and internally the compiler is doing this. That's what the compiler is doing. But it's neat because you can use that and it saves you typing a lot and taking care about a lot of stuff. It's convenient. Some programs use that, some don't. Long ago, you gave an analogy. It is fair to say that for both C++ and Rust, ampersand is map and star is key. I'm not sure if that analogy is right or not, but whatever analogy you have in mind, it should apply to both, because the logic is the same for both. It is the same logic. So if the analogy works for you, it should work for both. I'm not able to follow that analogy. Ampersand for map, star the key. Yes. For me. Yes. For me, value is the host, and ampersand value is the address of the house, like avenue of the captain 55. Yes, ampersand lets you know. No, ampersand lets you know where it is. So ampersand where it is. star, go where it says. You should write an actual value that is named house, and when you talk about that in your book, okay. But don't talk about Windows. That was confusing. They work similar. They work similar, Windows and Linux, but not exactly equal. But the thing is that when you write stuff, you know what is the problem. You know what is the problem, that all operating systems that are Unix based, they work pretty similar, very close. macOS, Unix, Linux, BSD. The memory layout is very similar. You mean the ones made from glass? I use that in analogy, like in a window. Oh, yeah, that is a bad analogy. That is a bad analogy. Okay. But yeah, so the problem is that memory addresses also have a memory address. This is more complicated to get an analogy for. So treasure box, I don't know, is, so if we put a percent value is where the address is where we store the address of the house. For example, PO Box 55. So like you have another address where we store addresses. So in that address, we store the address of the house. And we can go forever. Percent gets you there. A star lets you open it. No, but no. You have the bad analogy here. A percent is not to get there. Is to know where it is. It doesn't mean going there. It means where it is something located. Where is the address of something? So like the address of my house doesn't get you here. You need to travel to come here. That's a different action. So a percent my house is the address of my house, which is just a text that says this address blah 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 Ireland. Okay. And with that, if you use a star, you can go and come here. The action of going is the star. A percent only gives you the information. Okay. There are too many ways to interpret stuff, so I'm not going to fight over this because, I mean, maybe your understanding is correct. We might have just different ways of wording the same thing. That's totally fine as long as you understand it. Yes, but seeing the house is on the star part. Traveling is on the star part. The ampersand is only the address. It's only the address. Nothing else. Nothing more. It's only in our case, in the computer, is only a number. In the physical world, is just a text, and that's it. What do you want to do with that? You might want to store it. You might want to share it. You might want to, don't know. But yes, a person is required to get there, because you need to know where to go in order to get there. But a star gets you there. Ampersand tells you where to go. Where to go, and this is to get there. If that makes more sense, I don't know. This kind of stuff is pretty tricky for everyone. For everyone. I remember that I helped other people lots of years ago with C classes, and they were having huge amount of trouble understanding this concept. Is this star a map? No, it's not a map. It is not a map. It's not a map. Huh. Now I am understanding your analogy. Because a map is key value. A star is address to value. Kinda. Is not an analogy that I do like. I don't like it. But I cannot tell you that it doesn't work. It does work. It has some similarities. It does have some similarities. But wait. I do have another one. Let me create the whole computer memory. So let's say that we have a unsigned char, RAM memory, and this contains 4 billion values. Okay, you don't like that. You're not like Rust. You're not smart. You're stupid. Okay, wait a second. So when you put a value into your memory, okay, what you're doing is the value equals, so when you do value equals 55, what you are doing is that so ampersand value is the index in the vector of memory, and are the contents. When you do star value, you are accessing the so you are doing so for star, or let's say reading. I don't want to get all. What you're doing there, what you're asking is to the vector that is the RAM memory, you are placing here value. Or if you do star value plus equals 2, you are doing that. So you're using the contents of the variable as the memory address, like the index, the position in memory on what to access. So this is very similar to your map analogy, but instead of a map, I'm using an array. The reason is that the memory works like an array. The memory does not work like a map. Although the analogy is very similar, for map works quite well. The thing is that thinking about it as an array is much more closer to the actual reality. This works much closer to what the hardware is doing. So yeah. And I'm not sure if I can make an analogy with server somewhere. I don't know how that will work. I don't know if you can give me some ideas, or I'm not sure. Like a hotel, for example. So let's say you have a hotel. So you have a room. Okay. Yeah, I don't know. But this is not the room ID. This is the room, the contents of the room. Which is, I mean, putting contents of the room as a number is strange. Room tenants, okay. Or room in use. Let's put this as a boolean. Maybe it makes more sense. Okay, and then if you do that, maybe room 505. Then if you do double, it will be where the info of the room is stored. Okay, like the locker for keys or info. Okay. So welcome back. So here is my example in like using hotel rooms. So you could have a boolean of, is the hotel room in use? True. The memory address of that could be that the address is room 505. If you take the memory address of the memory address, that could be, for example, where the information of the room is stored, like where is the locker for the keys, or in which folder is stored the information of this room. If you do, for example, a pointer to room, you could say that you want to store the memory address 505 into here, and when you do start room equals false, what it's doing is get the room ID stored in the room var and mark it as free. So it will go to the room 505 and mark it as false, not in use. This is the alternative idea. I don't know. It could be analogies all day. This is something that you will get more confidence in as you use it. So now that you are working with C++, you will get to understand this better as you are forced to use pointers. As you use functions like those things that you have to put a star and ampersand and so on to modify the contents, you will get more practice and a better understanding with it as you work with them. The other thing I can talk about is in structs or class, it doesn't matter. So in a struct, I don't know, in the ID struct test. So if you have an owned value, you use dot. So if you have was this the correct syntax? Yeah, seems so. In contrast, if you have a pointer, borrow in Rust. Yes. I was thinking of closing already. You use the arrow. So because P is a pointer, then you use this to do that, which translates to basically internally this translates to star P dot ID equals 1. So yeah, that's for you to know. Like in C and C++, you have the arrow for you when you have a pointer to a struct or to a class, doesn't matter. You have the arrow to avoid having to write that. So arrow instead of dot. Yeah, that's what it does. So yeah, and this is enough for today. Like I covered all the ground that I wanted. Seriously, for the next time I can try to explain lifetimes in Rust using this knowledge here. Because I can next time I can try to make some code in C++ that can be broken very easily by mistake, and how in Rust you have lifetimes and prevents you from breaking it, because this mambo jango of pointers, addresses, and their references is super helpful, but it's also super dangerous, because one mistake and you are out of memory bounds and you're writing the wrong thing. In Rust, the same thing, the compiler will catch it, and that's thanks to the lifetimes. That's why the lifetimes are there, to allow you to do this stuff safely. Okay, so I think this is enough for today. Thank you very much, Jorge, for being here. It seems that was helpful, and I hope you can use this for your adventures in C++ in Rust. So, with that, we end the stream. Thank you very much. Okay, good night.